front row, you will not be called on. See, you heard me. And Duncan says he's very loud. Bill. Oh. There is a seat right here. Right, yeah, there's some over here. Oh, there. Can you see what happens when you get there? I know you. Okay, is everybody comfortably settled? Excellent. Right, well, we're going to start on the dot for once. Too bad for the stragglers. My name is Corinne Horowitz. I know many of you who know many of me. And, oh no, one. Yeah, I wish I could call myself every so often, but it's not going to happen yet. Anyway, I am the president of the Friends of the Goleta Valley Library, which is a fundraising arm of the Goleta Valley Library. And thanks to our group, and I would like everybody who is a friend here to give themselves a huge round of applause. And I hope the ones who didn't applaud themselves will join us. So we gave almost $100,000 last year to the library. We opened the new room in the children's section. We keep the library open 7 days a week. We are the only ones in the area. We give funding for everything from new computers, to chairs, to cards, to all the children's programs, all the gigos for the summer reading program. If your children and grandchildren are not doing it, please have them follow our reading program, because we bribe the kids to read and it works. I know that they should do it because they all love reading, but it's amazing what a bouncy ball can do. So bring them over, we'd love to have more kids. Our program of lecture happens about 9 times a year. We don't do anything in the summer. The next one will be in September and will be on art history. It's all very varied topics. And we have wonderful speakers who are experts in their fields. And every so often, we get the absolutely extraordinary professor who comes from out of town, and instead of going to the beach, he does a lecture. So it is my great pleasure to thank Professor Duncan Brown, who normally lives and professors at Syracuse University in New York State. He is here for a 2-month program at the Kavli Institute for Theoretical Physics on the UCSB campus, and his topic is particularly interesting. As you know, there was lots and lots of new research that was done recently on gravitational waves. So, thank you so much, Duncan, for talking to our audience, and I will leave you at it because otherwise I will embarrass myself profusely while trying to describe what he does.
Okay, so thank you for inviting me. So what I'd like to talk to you about today is I'm a gravitational-wave astronomer. What that means is I use gravitational waves to study the universe. I used to be a physicist working on a big project that was trying to make a discovery, and then that project actually saw something, so now I'm an astronomer and I can actually look at it. So I started my career as a gravitational wave physicist, and now I'm a gravitational wave astronomer. So what I'd like to talk to you about is this new field that's really opened up since 2015, but is a field that's been over 100 years in the making. So where does it start? It starts with Einstein. So our understanding of gravity stretches back many, many years. So there's the apocryphal story of Newton, apple falling on his head and writing down a theory of gravity, and it's a bit more complicated than that. But Newton wrote down a theory of gravity that serves us pretty well in our everyday life. So if you want to, if you're walking around on the Earth, you typically walk fairly slowly. Not many of us walk close to the speed of light. You typically don't have that much mass, you don't have that big a gravitational field, so you're not in the regime where you're so heavy that you're starting to bend space-time. If you're wandering around in, around fairly low mass objects like the Earth, if you're wandering around at speeds much slower than the speed of light, then Newton's theory of gravity is a pretty good way of describing gravity. It will predict the results of experiments you want to do. If you want to know what the force between two objects is, it's the mass 1 is the product of the two masses divided by the square of the distance between them, times a constant, which we call Newton's constant, that tells us how strong gravity is. So that's an experimental thing we measure that tells us how strong gravity is. But the problem is, if you start to get into situations where you're no longer moving slowly, you're no longer in a regime where the gravitational field is pretty weak, Newton's theory starts to break down. The predictions it makes start to be wrong. And this was known about for a while. So you don't have to go that far from the Earth, relatively speaking, to start to see Newton's theory of gravity breaking down. If you try and predict how Mercury orbits around the Sun, you find that Newton's laws don't exactly predict how Mercury orbits around the Sun. There's a discrepancy, and this was known for a long time. And this was an unresolved thing in Newton's theory. It wasn't until Einstein came along, and Einstein built on the work of many, many other people leading up to his great discoveries. So he looked at results that experimenters had made. He looked at observations that astronomers had made. He looked at work that mathematicians had done to kind of put physics on a firm theoretical framework. And Einstein, after building on all this work in the community, he wrote down what's called his general theory of relativity, which is our current modern picture of how gravity behaves. And Einstein's general theory of relativity is much better at predicting what's going on in situations where you're moving very fast, close to the speed of light, and that you're dealing with strong gravitational fields like you might get near the sun. One of the predictions of Einstein's theory of relativity is that in strong gravitational fields, time actually slows down a little bit relative to someone who's in a weak gravitational field. You can see this with atoms jiggling around on the surface of the sun. Their clocks seem to run a little bit slower than the equivalent atomic clock here on Earth. So we've tested Einstein's theory of general relativity in a bunch of different situations. So famously, Eddington's theory to see the bending of starlight around the total eclipse. That was a prediction of Einstein's theory of general relativity, that gravity would actually bend light, and you could see starlight bent around the sun. If the moon was blocking out the sun, you could see that starlight being bent. That was a famous experiment that was done about 100 years ago. So there have been lots of experiments that have tested Einstein's theory of general relativity. Physics is all about making predictions that then you go out and experimentally verify. If your theory makes a good prediction, it can be experimentally verified, then you have a good theory. If it doesn't make a great prediction, well then you need to go and revise your theory. So experiment leads to theory, which leads to experiment, which leads to theory, and that's how our knowledge progresses in physics and in astronomy. One of the great things about doing astronomy is that your lab for understanding the laws of physics is no longer just the lab you have on the Earth. When I teach Astronomy 101 in Syracuse, I start my Astronomy 101 lecture actually with a picture of Auguste Comte, who was a philosopher of science who lived in the late early 1800s. And one of the things he said, this was in the great expansion of human scientific knowledge, one of the things he said is, we will never know what the sun is made of. He's asking the philosophical question, are there limits to scientific knowledge? Are there things that we won't know? And he postulated, we will never know what the sun is made of. Turns out it's only a handful of decades later that it was proved wrong, and people realized, we could use spectroscopy, we could observe elements on the surface of the sun, we could link those to what's going on in the lab, and we could study distant objects. So when you're doing astronomy, when you're doing astrophysics, part of the reason we do it is because it's cool, right? I mean, looking at the stars and looking at black holes is pretty fun. But one of the other reasons we do it is that the universe, if we can understand what's going on, the universe becomes a laboratory that we can use to do experiments to advance our knowledge of physics, which helps us here on Earth and our general understanding of our place and where we're going. Okay, so that's kind of the introduction of what we're going to talk about. What is Einstein's theory of relativity? Well, Einstein's theory of general relativity can be captured in a couple of sentences, thanks to John Wheeler. It says that matter tells space how to curve, and space tells matter how to move. So this is the picture that we have when we think about general relativity. These balls are supposed to be objects of different masses. and this grid here is supposed to represent space, the space that we live in, really space-time that we live in. And you can't see space, you can't see the curvature of space. But if you could visualize it, you would see that the more massive object bends space more than the lighter objects. So that's mass bending space. That's the picture we have in general relativity, that matter causes a bending of space. And space tells matter how to move. You can imagine if you flicked a ball bearing along here. So imagine have a trampoline, you put a bowling ball on it, it bends the trampoline. If you flick a ball bearing along, as the ball bearing runs through the curvature, it's going to be deflected like this. And so even though the ball bearing isn't in contact with this, it's seeing the curved space, and it knows that it should move like that. So that curvature of space tells matter how to move. So this is our theory of general relativity. And it's been tested very, very well up until 2015 in what we call the relatively weak field. So strong enough that Newton breaks down, but not the really extreme gravity where Einstein's theory starts to make really interesting predictions. And one of the really interesting predictions Einstein makes is if you get enough matter in a small enough region of space, then there is no force of nature that can overcome the pull of gravity pulling that matter down into denser and denser and denser space, denser and denser space. And this happens in the universe when stars die. If you have a star, so a star like our sun is basically it's a giant thermostat. So in the core of the star, there is a really, really dense region that contains a lot of hydrogen. And the sun is so dense and so hot inside that you actually get these hydrogen atoms fusing into helium atoms, nuclear fusion that creates energy. That energy pushes up and pushes up against gravity and stops the sun collapsing down. So gravity pulls the material, the sun's gas down, which heats it up, and then the nuclear fusion that gets ignited because it's being pulled down pushes back out. So the sun works like a thermostat. If it contracts a bit, it heats up, which pushes it back out, and it sits roughly stably at the size of the sun, burning for billions of years. But when a star exhausts its nuclear fuel, as gravity starts to pull it in, it doesn't have enough energy in the core to push back out, to generate heat that pushes back out. So the core starts to collapse down, and you can reach a point where the material in the core, you pile up so much dense material in the core, stellar ash, basically iron, that you pile up so much of this material that the forces that stop, there's a force that stops my hand from going through the table. It's the repulsion of the electrons in the bottom of my hand with the electrons in the top of the table. So I can't push my hand through this table. But if I pushed hard enough, if gravity pulled down hard enough, it could actually push those electrons into the protons in the atom, merge things together, keep pushing, keep pushing, keep pushing, everything collapses down, and there's no force that can stop that matter collapsing down. And when that happens, you end up with a black hole. So this is a diagram that shows the space-time curvature around a black hole. So this is kind of pulled infinitely far down, and we have no idea what goes on down here infinitely far down. That's a regime where Einstein's theory breaks down. We don't know what happens in the middle of a black hole because Einstein's theory breaks down in those types of regions. So this is an area where we've advanced from Newton to Einstein, but our knowledge is incomplete after that. But the universe, we think, can make these black holes. When stars die, when a massive enough star dies, we think it can make these black holes. And we think we've seen evidence for these black holes, strong evidence for these black holes in traditional electromagnetic astronomy. So radio waves, we've seen objects orbiting a massive black hole in the center of our galaxy, so you can watch stars orbit an object that sure is behaving like a black hole in the center of our galaxy, but you're not seeing the black hole itself. So what might you do to go out and look for black holes directly, to see a direct effect of the black holes where you're really touching these things with gravity? Well, one of the predictions of Einstein's theory of general relativity is gravitational waves. So gravitational waves are kind of like light, radio waves in many ways. So gravitational waves are caused by mass moving around. One of the predictions of Einstein's special theory of relativity, which is his theory without the gravity, is that nothing can travel faster than the speed of light. No information can travel faster than the speed of light. What that means is if I speak into my cell phone, electrons move around in this metal strip on the edge of my phone, which is the antenna of my phone. So as I speak into here, there are electrons jiggling around in here. The computer inside here causes an electrical current to jiggle around inside here, which changes the electric field in this room. Now, if stuff could propagate faster than the speed of light, everybody in the universe instantaneously would see the changing electric field. But nothing can travel faster than the speed of light, so in particular, the information about the electrons jiggling around in here travels out at the speed of light in the form of radio waves. Radio waves are a form of light. The electrons jiggling around inside the projector in here are generating a changing electric field. That changing electric field is propagating out at the speed of light to the board. So as I move charges around in electromagnetic theory, as I move electrons around in electromagnetic theory, moving those electrons around creates a change in the electric field. The information about that changing electric field propagates outwards into the universe, propagates out at the speed of light until a distant observer sees it. Einstein predicted that the same type of effect that people had studied for many years with electricity and light also happened in gravity. If I have a mass, it generates a gravitational field. If I move that mass around, then if things could travel faster than the speed of light, everybody in the universe instantaneously would know that I've moved that mass around. But that would violate special relativity. Einstein predicted if you move masses around, and you have to move masses around in a certain way, if you move masses around, I'm doing this, this is one of the ways that you have to move the masses around. If you move masses around in a specific way, then that generates a change in the gravitational field, and the change in that gravitational field doesn't travel ever in the universe instantaneously. It's carried out at some speed, and that speed is also the speed of light. So if I move masses around, it generates a changing gravitational field that propagates out the speed of light, and those waves of gravity, gravitational waves, behave in many ways like light. They behave like light. So they travel out in the universe. If I want to study the sun, I look at the light coming from the sun. If I want to study black holes, then I want to look at the gravitational waves that are coming from those black holes as they move around each other. So what do I mean by that? Okay, so in our universe about 1.3 billion years ago, this is an artist's impression based on a computer simulation. So about 1.3 billion years ago in our galaxy, this is an image showing what it would like if you were close to two black holes. So these are two black holes, and they're bending starlight around them because their gravity is so intense that the starlight is being bent around them. And these two black holes are in orbit around each other, just like the sun is in orbit around, the Earth is in orbit around the sun. So these two black holes are orbiting around each other. They spin around like this. So there's two black holes spin around each other. The two black holes spin around, and they're generating gravitational waves. So as these two black holes move around, the information about the changing shape of the black holes is propagating out at the speed of light, propagating out as gravitational waves. Now, just like light carries energy, you can feel the light. I live in upstate New York, so all I have to do is walk out here and I can feel the sun's energy on my face as I burn. As you know that light carries energy. Just as light carries energy, gravitational waves carry energy. These gravitational waves are carrying energy away from this system of two black holes orbiting around each other until eventually the black holes crash into each other. So this happened in our universe about 1.3 billion years ago. So why do we care about that? Well, the gravitational waves that these black holes generated could be detected by us here on Earth. So this is a cartoon showing what's going on. This is the space background again. So these are two black holes shown in here, and this is an artist's visualization of what the gravitational wave would look like coming out of these two black holes. So I have two black holes moving around each other. So now I just don't have that kind of static throat of space-time curvature where the black holes are. I have these two throats moving around each other, generating ripples in the fabric of space-time that are propagating out at the speed of light. So these ripples are gravitational waves, and they carry information about the sources that generated them. Just like sources of radio waves, sources of light, carry information about the source that generated those radio waves, these gravitational waves carry information about these black holes that generated them. So if we can detect these gravitational waves, we can use them to study the sources of the black holes, to explore the black holes directly, and to do a completely new type of astronomy. Okay, so what are gravitational waves and what's their physical effect? A gravitational wave is a consequence of masses moving around, changing the gravitational field, and that the information about that changing gravitational field propagates out at the speed of light. But how do I actually interact with gravitational waves? With light, I know how to interact with light. Nature has evolved a system of interacting with light in the front of my head. So I can see there is light coming out of there. So it's pretty easy to detect the light coming out of that projector with the eyes in my head. If you want to look at light from distant stars, you have to build telescopes. You have to do more advanced work to really reach out in the distant reaches of the universe. You can look at light from radio waves all the way up to gamma rays. So how do we actually look at the universe using gravitational waves? Well, first we have to think about what the physical effect of a gravitational wave passing through us is. So a gravitational wave passing through us, the effect of a gravitational wave is to stretch and squeeze space, as shown in this ring here. So if you imagine you had a ring of masses floating in space, and a gravitational wave passed through this ring, so this is a gravitational wave passing through the screen here, the effect of this ripple in space-time is to stretch space in one direction and squeeze it in the other direction, and then it repeats it with the stretching and squeezing in the opposite directions. So the effect of a gravitational wave is to stretch and squeeze space. Now you might say, well, the fact that I'm sat in this room right now and I don't feel like I'm being, if someone stretched you, if someone grabbed your arms and pulled, you would feel it, right? So you would feel the stretching and squeezing if a gravitational wave of this strength was passing through the room right now. It'd be pretty unpleasant for us. I'm going to give you an idea. I'm going to quote a number that I'm going to call the strain of a gravitational wave. This is the change in length divided by the length. So if two people grab my arms and pulled, and stretch out my arms by a factor of 2, then I get a strain of 2, right? So it's the change in length divided by length. The stronger the strain, the more stretching you feel as someone pulls on you. So how strong are gravitational waves? It's pretty easy to generate light, right? We all have devices that are in our pockets that you can move tiny electrons and generate detectable amounts of radio waves. You can generate light in this projector. Matter and the electromagnetic field couple quite strongly. It's pretty easy to make and detect light. The problem with gravity is that it's really, really hard to generate gravitational waves, and it's really, really hard to detect gravitational waves. Gravity and matter couple much, much, much more weakly than light and matter. And this is to give you some idea how. So the strain that I'm looking for, the strength of the gravitational waves, so the amount of stretching, goes as Newton's constant, which remember told me how strongly gravity and matter couple together. That's a very, very small number, so 0.0000007, right? Then I take that tiny number and I divide it by the speed of light to the 4th power. The speed of light is a very big number. So I multiply 300 million by itself 4 times and divide this tiny number by this huge number. And then I also have to worry about how far away the source of gravitational waves is. So the energy in the object, the amount of energy in that circular motion in the object, gives me the strength of the gravitational waves. For an object that's out there in the universe at astrophysical distances, this is the distance, so I divide by the distance of the object, and that's a very, very large distance, 3 followed by 23 zeros meters. And the reason that I'm looking at objects very, very far away is these two numbers here fight with each other so to generate a really, really small number. So the strength of generating, it's really, really hard to generate gravitational waves. Said another way, space-time is very stiff. It's really hard to get that energy into space-time to generate these gravitational waves. So unlike in the 1800s, where people did laboratory experiments, so Hertz and Faraday, and people did experiments with light, electricity, and magnetism, they could do that in the lab. They could do it on the tabletop. You could generate light, you could receive light, you could generate radio waves, you could receive radio waves. You can't do that physically in the lab. You can't build a tabletop generator and detector of gravitational waves that you can do any meaningful experiments with. So you have to look, in order to overcome this tiny number here, you need a huge amount of energy, which means you're looking at stars, black holes, neutron stars out there in the universe, massive amounts of mass packed into very small regions, moving at significant fraction of the speed of light. So you need this number to be huge to overcome this, and if this is huge, it's not going to be in the lab, it's going to be far away out there in space. So it's really, really hard to generate, and so it's also hard to detect gravitational waves. So this is a cartoon that the Ligo project made that shows the effect of gravitational waves. And you see these, you can't really see them, but they're visualizing the gravitational waves passing through the Earth, and they say that the gravitational waves stretch and squeeze the distance between objects, and so the gravitational waves passing through the Earth causes stretching and squeezing, and it looks like this. Then they note here, scale of effect vastly exaggerated. How vastly exaggerated? Well, the change in length is 0.00000000001, right? So this is a tiny, tiny change in length. So a reasonable physical gravitational wave that you might hope to detect on the Earth is the strain is absolutely tiny. So to give you an idea of the experimental challenge of doing this, and this is why it took 100 years from Einstein proposing the existence of gravitational waves to actually being able to detect them. To give you an idea of detecting a strain of that tiny number, of 10 to the minus 21, 10 to the minus 22, that's equivalent to measuring the distance between the Earth and Proxima Centauri, the nearest star to the Sun. So Proxima Centauri is a distance of 4.2 light years away from us. So the nearest star to the Sun is about 4.2 light years away from us. Measuring a strain of 10 to the minus 21 is equivalent to measuring this distance to a precision of 10 microns. So measuring the distance between the Earth and the nearest star, smaller than the width of a human hair, right? That's the measurement challenge we're talking about here. So you might say, well, there's no point doing this, just give up. And Einstein did. Einstein said, there's no way we'll detect these things. In fact, there was an argument for 50 years about whether it was just a mathematical artifact of the theory that wasn't solved until the 1950s. In the 1950s, Felix Pirani set up a thought experiment backed up with some mathematics that said, no, gravitational waves carry energy just like light does. They're a real physical effect. They're tiny, but they're real. And we might be able to detect them. And Joe Weber, who was one of the early pioneers of the field, who unfortunately didn't detect gravitational waves, but was one of the pioneers of the field, he walked out of that meeting and said, I'm going to build a gravitational wave detector. And that was in the late 50s, and it took another almost 50 years to get from that point to actually detecting these things. And this is why. So what are the machines that we use to detect these things? Well, this is Ligo. This is the Laser Interferometer Gravitational Wave Observatory. This is what a gravitational wave telescope looks like. So what's in here is there's a laser and some mirrors in here. I'll explain this a little bit. There's another mirror right here. This is a 2.5 mile long steel beam tube that has a laser beam in it. And over here, 90 degrees, is another 2.5 mile long tube that houses the other half of the beam. And so this is a huge scale here, so this is big science. And what happens is, as a gravitational wave passes through the Earth, these arms get stretched and squeezed, and that's how we sense the gravitational wave. Now, the problem is there's a lot of ways that, I'll explain how this works in a bit more detail, but basically there's two mirrors hung here and here, and two mirrors hung here and here, and you're using a laser beam to measure the distance between those two mirrors to look for the stretching and squeezing of the gravitational wave. But there's lots of things that can make those mirrors move around. So it's very challenging to do this. So one of the things that Ligo did from the get-go is they said we're going to build two detectors. One of these is in Hanford, in Washington State. This is southeast of Washington, the desert. This is the other one in Livingston, Louisiana. So this is a close-up view. This is a concrete beam tube to stop people shooting at the bullets from hitting the detector, because people hunt deer around here. So there's stray bullets from deer hunting. So this is a concrete shield, and inside here is a steel tube. Actually, Hanford took the most punishing. So Hanford's on the DOE nuclear site, up at the Hanford Nuclear Reservation. People have taken pot shots at this, but in Hanford somebody drove a truck. Fortunately, they weren't hurt, but there was a map that hadn't been updated showing that the Ligo beam tube was running across it. And some DOE security guys were barreling across the desert and then drove right into took a jump and drove into the beam tube. Fortunately, they were fine, but they got a nasty shock. But that's why this is concrete right here. Inside, there's a steel beam tube, and this is the corner station that you saw where all the lasers and stuff are. Okay, so we have two of these. The reason we have two of these is so you can be sure that any tiny little signal that you pick up, these things are separated by thousands of kilometers. They're at opposite ends of the country almost. And so the reason we have two of these is so if you see a signal, you see it in both detectors, you have confidence that this is real, right? That you have confidence you've seen a real signal if you see it in detectors separated by thousands of lights. Okay, so how do these things work? Well, this is a simplified picture of what happens inside Ligo. This is a laser right here. And what happens is a laser shines, so the L shape here is the arms you saw. This is what's happening inside the beam tube. So a laser shines a beam at a beam splitter that sends half of the beam this way and half of the beam that way, and then recombines it. So laser light comes in, travels along those arms, and then hits a mirror that is at the other end of that 4-kilometer long arm. So the laser beams come back here towards the beam splitter and recombine at the beam splitter. And if the arms are exactly the same length, this is set up so you get what we call destructive interference. The peaks and troughs of the light cancel out. But if the arms move relative to each other, you don't get perfect interference here. You get some light leaking out towards the detector. So if the arms are exactly the same length, which is what they try and maintain, you get no light coming out. But as the gravitational wave goes past and stretches and squeezes those arms and changes the arm's length, you get light leaking out here towards what we call the dark port of the interferometer, because normally it should be dark. There should be no light coming out here. But as the gravitational wave goes past, let me show that again. So so the beam comes back here, reflects back, and as the gravitational wave goes past, it stretches and squeezes the arms, and you get a signal coming out here. These flashes of light are the signal going through. So basically, you're using laser light as a very, very accurate ruler. That you have 4 kilometers this way and 4 kilometers that way. You use the laser light to time how long it goes there and back again, recombine. If the arms are exactly the same length, no signal. As a gravitational wave goes past, it stretches one arm, squeezes the other arm, and so you get a signal coming out. Now the challenge of doing this, this picture makes it look fairly simple. And LIGO is an experiment that, the core of the LIGO experiment is something that people see at undergraduate or maybe even high school kind of tabletop experiments of what's called a Michelson interferometer. But the problem is these mirrors are hung on the surface of the Earth. So these mirrors are sat in Washington and sat in Louisiana, and Interstate 10 goes past the Livingston site in Louisiana, and trucks drive past on Interstate 10, and ocean waves hit the Gulf Coast, or the Pacific Northwest occasionally has earthquakes. There's all different kinds of noise sources that are out there that could cause those mirrors to shake around. And don't forget, I said, to put it on this scale, the length change caused by an astrophysical gravitational wave on the 4-kilometer arm is moving the arm smaller than the size of a proton. So smaller than the size of a nucleus of a hydrogen atom. Right? That's the equivalent to saying, Earth to Proxima Centauri to the width of a human hair. The distance you're actually measuring is 4 kilometers, 2.5 miles, and that distance is being sensed to a size that is smaller than a proton. Right? So the surface of the mirror that you are trying to bounce that laser beam off has atoms on it that are jiggling around, and that jiggling is bigger than the distance that you're actually trying to measure. Right? So there are all kinds of noise sources in this detector that hide that tiny gravitational wave signal, and what a lot of effort has gone into is minimizing those noise sources in the detector, and then also making predictions what the gravitational wave should look like using theoretical models of gravitational waves, so we can pull those models out of the detector. This is what it looks like. It's not quite as simple as the cartoon. This is one of those mirrors at the end. This is two of the commissioning teams shown for scale. So these things are hung from many, many layers of seismic isolation, active isolation, and try and, these things are like a giant pair of noise-canceling headphones. They sense the motion, the local motion, and then feed that back to the mirror to try and keep that mirror as still as possible. So all the environmental noise sources are isolated from the mirrors. So we worked for many years to build these detectors. In 2015, what are called the advanced LIGO detectors. We had a whole generation of first-generation detectors that were a technology prototype, a kilometer-scale technology prototype. 2015, the advanced LIGO detectors turned on for the first time in September 2015, and literally like the day after we turned them on, we saw this. Play this again. So this signal here is, you can hear the whoop. Listen very carefully. Whoop. So what this signal is, remember that movie I showed you of two black holes a couple of billion years ago going around each other and crashing into each other? This is the last fifth of a second of that happening. So these are the gravitational waves. This is the LIGO Hanford detector. This is the LIGO Livingston detector. What this is shown here is the time, and then this shows the gravitational wave frequency. as those two black holes from that movie orbit around each other, they give off gravitational waves. The frequency of the gravitational waves they give off increases as they get closer and closer together, and the black holes start to move faster and faster and faster, until eventually they go ploop and collide into each other. And that makes a sound. So gravitational waves are like listening to the universe, because it's ripples in the fabric of space-time. So it's like hearing the universe. Light is seeing the universe, but gravitational waves are ripples in the fabric of space. It's like hearing the universe. Those gravitational waves generated by those black holes are in the roughly audio frequency bands. You can hear them. And what you hear is whoop, as these black holes crash into one another. So the day after we turned the advanced LIGO detectors on, roughly 100 years after Einstein had predicted gravitational waves, people had argued for 50 years whether or not they really even existed, and then people had spent 50 years building detectors sensitive enough to pull these signals out the noise. People have spent time modeling these signals, developing analysis techniques to extract signals from the noise. Literally the day after we turned them on, we saw this whoop binary black hole signal. So two 30 solar mass black holes, so two black holes about 30 times the mass of the sun, crashing into each other at significant fraction of the speed of light, about 90% of the speed of light. So this is a huge, huge, huge collision of two black holes crashing into each other, generating gravitational waves that propagated across the universe for billions of years until they passed through this detector that we just built like the day after we turned it on. You can say we got lucky, but really, we got out to a region of space where, we got the universe is good at producing black holes and good at producing binaries, and these things happen at a fairly high rate. Right now, the advanced LIGO detectors are operating with even better sensitivity than they operate right now. We're seeing about a black hole a week. Right? So LIGO is producing alerts. In fact, one came out this morning. So this morning, as you were preparing breakfast, two black holes collided. Well, the two black holes collided many, many years ago because things travel at the speed of light. But as you were preparing breakfast this morning, the gravitational waves from two black holes colliding passed through you, passed through LIGO, and that generated an alert that was sent out. So these things are happening about once a week at the moment because we've made these detectors. Yeah.
If more than one black hole formed at that time, what would it do?
So if more than one black hole collided, if more than one collision happened at roughly the same time, so the waves arrived on Earth at the same time, it would make the signal extraction process more complicated because the two waves would just be added together, right? So they'd just be added on top of each other. So what LIGO would see would be the sum of those two gravitational waves. The events are still sufficiently rare at the moment. One a week is not that rare. But they're sufficiently spread out at the moment that they're not piling up on each other. But future generations of gravitational wave detectors, as we make them more sensitive, they're going to have to worry about that. They're going to see signals piling up on top of each other, and you're going to have to extract multiple needles from the haystack at the same time, rather than extracting one needle from the haystack. So, yeah.
So the final, I don't know what to call it, absorption event of the two black holes orbiting one another takes approximately 0.2 of a second.
So that is these black holes have been orbiting each other for billions of years. But the further apart they are, the lower the gravitational wave frequency, the slower they go. And when they're at large distances apart, the gravitational wave frequency is too low for LIGO to see. So LIGO has a sensitive frequency band that is basically about the frequency band of the human ear, just by happenstance. The LIGO really can't see gravitational waves below about 10 hertz, because below about 10 hertz you get swamped by seismic noise, other environmental noise sources, and the upper end where LIGO can see is about 3 kilohertz. So basically, roughly, not the lower end of the human audio spectrum. When the gravitational waves when the black holes were far apart, the gravitational waves they were producing were below 10 hertz, and so LIGO couldn't see them. They were hidden in the noise. They were passing through us, but it was like this low rumble that's building and building and building and building until the frequency and the amplitude gets into the sensitive band of the LIGO spectrum, and LIGO sees just that last whoop, the last fraction of a second of the black holes merging. The rest of the waveform is here, going back to when the binary formed, but it's too low frequency and too quiet for LIGO to actually see it.
So is this a repetitive event that's occurring repetitively because they're still in orbit?
No, these are, so after they hit each other, that's it, they're done. Right? They hit each other at the end here, this pair is done, they form a single black hole that just sits there, done. Not emitting gravitational waves anymore. But somewhere else in the universe, there's another pair of stars that are doing this, and you've seen the last few minutes. Yeah?
So that's like, you call it a wave, but it actually happens, and then there's no additional ripples or secondary effects that you could detect. When this happens, it's over, there's no other thing you can see happening. The wave doesn't
That's right. So
oscillate.
the wave goes back here, but once the two collide into each other, that you get a deformed black hole, and that deformed black hole, what we call rings down. It wants to get into a roughly circular state. So these two things come in, they form a single black hole, and then that very quickly rings down like if you hit a bell, right? The end of the waveform is like hitting a bell. You strike the bell, and you'll hear the bell ring down, and then the sound fades away, and then it's done. That's what's happening at the end here. So you get gravitational waves from the two orbiting around each other. They smash into each other. You get one black hole that's been hit as if you're hitting a bell. That last black hole rings down, and then it's done, and there's no more gravitational waves from that system. But there's lots and lots of stars out there in the universe, and so when I say these things are happening once a week within the volume of the universe that LIGO can see, we're seeing these stars crash into each other.
How big a field of view are you talking about?
So LIGO is more like gravitational waves like sound, LIGO is like a microphone. So the field of view is actually, it's like a microphone with an antenna pattern. So you can actually see up and down because the gravitational waves pass through the Earth.
So 360 degrees.
It's not quite 360 degrees, there's some dead spots, but it's effectively, it has all sky coverage.
Are Hanford and Livingston's both in the same?
Hanford and Livingston were by design aligned as closely as possible so that they would see the same signal. Up to the curvature of the Earth, they're basically the arms are aligned with each other. And that was deliberate to make the first detections and see the same signal. Yeah.
Is always two black holes orbiting each other, or actually can be more than two?
It's generally it's going to be binaries, not triples.
Okay.
A triple would kick the other black hole up, but I'll talk about something else that we've seen as well as black holes.
Sure.
Yeah. Okay, so one comment to say about this though is that I've talked about how hard it is to find gravitational waves, how weak gravitational wave events are. Gravitational waves are not weak, right? The luminosity of gravitational waves depends on this formula, right? So now my big number is on top, my little number is underneath, and so this is a big number here. This is the velocity of the system relative to the speed of light to the 6th power. This is the size of the system relative to something called the Schwarzschild radius squared. If I plug the numbers in for a binary black hole merger, then I actually get 10 to the 59 ergs per second. This is the luminosity, it's the amount of energy radiated per second in that binary merger. So 10 to the 59 ergs per second is the amount of energy radiated as those black holes merge. Compare that to the amount of energy the sun radiates. This is 10 followed by 33 zeros. This is the energy that the sun is putting out right now. This is the energy radiated in that binary black hole merger. This is 10 followed by 59 zeros. So gravitational waves couple weakly with matter, but they're not weak in the sense there's a lot of energy there. This binary black hole merger outshone all the stars in the visible universe as it merged because there's so much energy in that merger. Yeah.
Okay, well, what happens to all the other masses in the near field of this event? Are they affected in a way? I mean, you have a detector that's sensing minuscule amounts of this energy
Right.
in the near field. What's happening to a mass that's nearby?
Get exactly the same perturbations. You don't want to get too close to one of these things. you would be. It falls off fairly quickly, so you have to get pretty close to this. You would know there were black holes there if you were close enough.
Physically, would another mass be torn, distorted?
Even close to a binary black hole merger like this, it's hard for you don't get strong enough gravitational waves that you'd really get completely shredded, like falling into a black hole. But you would see a fairly large strain if you're close enough, and you would get stretched and squeezed. You would feel it. It goes as one over the distance. The closer you are, the more stretching you get. Yeah.
Do the gravitational waves bend around objects? Like if you had an eclipse of this event, something out in space is
Yep.
blocking it, it'll bend around, we'll
Yep.
still see it.
Gravitational waves are lens, just like
Okay,
lenses.
okay.
All right, so let me wrap up the black hole because there's one more thing I want to talk about. So this was discovered September 14th, 2015. It made press around the world. This is the signal that was seen, GW 150914, and this is a computer simulation of what this binary black hole merger looked like. So this is the gravitational waves. Remember, I showed at the beginning a picture with those space-time throats. This is a picture. So this is the curvature of space-time. This is a visualization of the two black holes. They orbit around each other. They're losing energy in gravitational waves. They're making this gravitational wave train here. They get closer and closer and closer together. And it's really this last part that LIGO sees. So this is the answer to the question, what's going on? This is the early part that you're seeing. They get closer and closer and closer together until eventually they're going to merge into one another in about 3 cycles time. So the movie slows down so you can see what's going on at the end of the waveform. And then you see the last couple of cycles, and then they pinch off and form one black hole. And then that black hole is the distorted thing that rings down like a jelly. You get this ring down signature, and then that's it. That's the last we see of them. So this discovery won Ray, Barry, and Kip the 2017 Nobel Prize in Physics. So this was a big discovery. So we had a pretty cool year, but it didn't stop there. One thing I've talked about is LIGO Hanford and LIGO Livingston. There are actually other detectors. Oh, this is out of date. Ignore this. I copied the wrong slide. Okay, so we have LIGO Hanford, LIGO Livingston, and the Virgo detector is not under construction. The Virgo detector is operating right now. So there's a French-Italian 3-kilometer detector in Italy, the Virgo detector. Calgary is under construction, and there's a detector planned in India. We actually have 3 detectors that operate as a worldwide network. GEO600 is a smaller detector that's a high-frequency detector that's not quite as sensitive. But these 3 detectors are comparable sensitivity, and they form a network that if you see a source, if you have 3 detectors seeing it, you can triangulate the source. So not only can you say where, that an event happened and read off the information about that event, you can say where on the sky that happened. Now, black holes are black, right? So knowing where on the sky a black hole event occurred may be not that interesting. But black holes aren't the only things that can produce gravitational waves. This is an artist's illustration of 2 neutron stars. So a star that is maybe about 7 solar masses, about 7 times heavier than the sun, when it exhausts its nuclear fuel, it's not heavy enough to form a black hole, but it can form something called a neutron star. A neutron star is about 1.5 times the mass of the sun, packed into a ball that's about 10 kilometers across. So basically a city-sized atomic nucleus. So all of the electrons are forced into all of the protons, and you just end up with 2 giant balls of neutrons that can be orbiting around each other. And so you have 2 massive city-sized atomic nuclei orbiting around each other about 1/3 the speed of light, giving off gravitational waves that can be detected by LIGO, and eventually these 2 things will crash into each other. If you smash 2 city-sized atomic nuclei into each other, you're probably going to get some pretty bright fireworks in the electromagnetic band, as well as the gravitational waves from the merger. So that's one of the reasons that we want to be able to localize the source. That you can say, we saw the gravitational waves before these things smashed into each other. Boom, they smashed into each other. They blow, they generate a huge amount of light. So where on the sky did that happen? Go look and point telescopes and see if you can see the light from this collision. And lo and behold, in August 2017, so right towards the end of the second observing run of ADVANCE LIGO, we saw this in the detectors. So this is the same type of thing I showed earlier. This is a time frequency diagram showing the output of the detectors, and the fuzz here is noise. But as this runs forwards, you can start to see, if your eyes look very carefully, follow this track right here. And then you can see the track here in Hanford as well. Okay, so that's the gravitational wave output of the Hanford Livingston, the LIGO Hanford, LIGO Livingston detectors, and the Virgo detector. that long track that lasted for many, many seconds is not the final fraction of a second of two black holes crashing into each other. That is the long, minutes-long final orbit of two neutron stars going round and round and round and round each other and eventually colliding into each other, being seen by LIGO and the two LIGO detectors and by Virgo. So let me picture. So as well as being seen by the LIGO and Virgo detectors, so this is what's called the Fermi gamma ray burst satellite. So there are satellites up there in space that look for bright flashes of gamma rays. Initially, gamma ray bursts were detected when the US was looking for evidence of Soviet nuclear explosions. They were looking for flashes of gamma rays, and they saw flashes of gamma rays coming from all over the place. Like, what's going on? What are all these flashes of gamma rays? Turns out they are astrophysical sources of gamma rays called gamma ray bursts. And a couple of seconds after LIGO saw that track of two neutron stars merging, the Fermi gamma ray burst satellite detected a pulse of gamma rays of right in coincidence and basically overlapping with the LIGO Virgo detector. And so this is what we saw. This is what we saw. So at 8:47 Eastern Time, in the LIGO Hanford detector, we saw a significant signal, high signal to noise ratio. We can read out the masses of this signal, so we know that the signal was 1.4 solar masses. That's much lower than black holes. So we think that that's a binary neutron star merger rather than a binary black hole merger. And we saw a Fermi gamma ray burst event 2 seconds after the merger. So we saw a gravitational wave merger followed by a flash of gamma rays. And this really set the whole astronomy community on edge, because this is the event that a large fraction of the community has been waiting for. One thing that was only seen in Hanford, even though Livingston and Virgo were operating, this is the signal seen in Hanford. This is the raw signal seen in Hanford. This is the track of that merger signature. This is what happened in Livingston. So I showed you that beautiful movie we made earlier after we cleaned up the data. This is what we actually saw in the morning. We saw a merger signal with a glitch in the detector. This is noise that happens in the detector. This glitch landed right on top of the signal and stopped us from getting a sky localization out quickly, triangulating the signal quickly. So we scrambled, we leaped into action. We had a team of people who worked on this. They basically removed this glitch from the data, just leaving the signal behind. And with this, we had a signal in Hanford and Livingston and information from Virgo that allowed us to localize the signal. These are my graduate students and former grad students and postdocs who worked on doing that. And at 1:54 p.m., we sent out an alert to the observing community to say, go look here on the sky. We think we've seen two neutron stars collide into each other. So they went out, and so this is a map of the sky. So they went out. This is the area of the sky that Fermi said the signal would lie in. This is Integral, another gamma ray burst detector, so not particularly wonderful localization. There's a huge patch of the sky to follow up. And so we went in with the LIGO and Virgo detectors, localized where this is on the sky. With just LIGO, you get these kind of strips on the sky. If you add in Virgo and triangulate the signal, you get this small region of the sky right here. And that was followed up. The galaxies within this region was tiled up by large telescopes all over the world. They followed up the signal until they found this galaxy right here, NGC 4993, that all of a sudden had a new bright source in the outskirts of that galaxy that had not previously been seen before. And what that was what we call the kilonova, the optical afterglow of two neutron stars crashing into each other. So when you take these two neutron stars and they crash into each other, all this neutron-rich material gets thrown off. So you get this huge amount of neutron-rich material thrown off that radioactively decays, producing light and gamma rays and all this other stuff. So this is the center of the galaxy of NGC 4993. This is the bright afterglow of that nuclear material thrown off by those neutron stars. And then after 14 days, it's faded back away. So it's faded back away. And this kilonova, what we have here, this kilonova signature, let's have a little animation of it here. So you see it, so this is 1 day, brightens, fades away, and then after 10 days it's faded away completely. And so this thing right here, this kind of orangey thing right here, is the kilonova signature. So that is the afterglow of two neutron stars smashing into each other. Why is that really exciting? Well, one of the things that you learn kind of in introductory astronomy is where do the elements come from? Where do the elements of the periodic table come from? You learned that the Big Bang makes hydrogen and helium. Hydrogen, a little bit of helium, but not much else. And then that hydrogen starts to form stars. Those stars burn that hydrogen into heavier and heavier elements. You make carbon and oxygen and nitrogen and most of the stuff that makes ours up. And then the stars explode in supernova, and that makes some heavier elements and pushes those out into the universe. And that all gets recycled and ends up being us. But when you do the calculations, you find that like some of the elements of the periodic table are missing in that process. And the elements that are missing are things like gold and platinum. The heavier R process elements, plutonium, other things are missing. And where we think these elements come from is right here. So what you're seeing right here is the kilonova afterglow of two neutron stars smashing into each other, producing all this neutron-rich material that is then radioactively decaying back down into what we call the R process elements, so elements like gold and platinum. So right now I'm wearing a wedding ring. This ring is made in something that looks like this. And I'll stop there. Thank you very much.
So what is it about the forces of this collision of the neutron stars that will produce these more exotic elements that...
It's a very neutron-rich environment. So these two neutron stars. So what happens is I maybe have an animation of these things colliding with each other. It's on my shirt. Okay. So as these two. So this is a computer simulation of two neutron stars crashing into each other, and they throw off what we call tidal tails. So they throw off this neutron-rich material right here. That material is much richer, and it has a much higher fraction of neutrons to protons than the type of material you see in supernova. So when you get this very neutron-rich material, you get a different set of decay processes forming because you build up elements that are in the R process group. It's basically the low number of electrons and high number of neutrons in this material that gives you a different class of elements. So in supernova explosions, you can produce lighter elements, but in the neutron star mergers, because you get this extremely neutron-rich material that you don't typically get elsewhere, then you can produce the R process elements. Yeah.
Is the 2-second delay due to the time needed for the flare?
Yep. So the 2-second delay is it's 1.7 seconds between when the two neutron stars, the end of the gravitational wave signal, so when the two neutron stars basically start to touch each other, and that system to assemble into something that powers the gamma ray burst. So what we think happened, we don't have good evidence because the gravitational waves disappear into the noise as they get to high frequencies. So we don't have gravitational wave observations of this. We'd love to have more sensitive observations of this, but we don't yet. What we think is that these two neutron stars for a brief time formed into a fairly large neutron star, but then that rapidly collapsed down to form a black hole. And it was that process of forming the large neutron star, collapsing down to a black hole and putting out these jets that took about 1.7 seconds. But that's one of the things we're doing in this workshop at the Institute for Theoretical Physics right now is discussing exactly how that happened. It's a very, very difficult problem to solve because it's so messy as to what goes on when these jets form.
How often do those occur, the neutron star collisions?
So we saw one of these in the second observing run. So by the time we've seen this, we'd seen about 10 binary black holes. We'd only seen one of these in the first observing run, so getting a rate with one observation is tricky. But the Ligo released an alert with a possible neutron star candidate in the second observing run. So it looks like the rate of these might be, maybe fingers crossed if I take the optimistic, one every few months, a few could be 12. You don't see as many, the universe produces more of these than black holes, but you don't see out as far into the universe for the neutron stars because they produce weaker gravitational waves. You don't see as far as you do the black hole. For black holes you can see way out into the universe, so even though they're rarer in terms of per unit volume, you see more of the universe, you see more.
How far back can you see the two black holes colliding?
So right now you can see out to about 500 gigaparsecs, so you're not back to the beginning of the universe type stuff. If you're looking at cosmic microwave background, you're looking at, you're looking at galaxies that are, you're not seeing the first kind of black holes form. We're not looking that far back yet. Third generation, right now one of the projects we're working on is, it takes 10, 20 years to build these detectors. So we're thinking about, what will be operating, looking at the gravitational wave sky in 10, 15 years time from now. That detector, we think, with a factor of 10 increase in advanced LIGO, that detector will be sensitive to see every binary black hole in the universe. You'll see all the way back to the beginning of star formation. So we're only a generation away from being able to see every single binary black hole in the universe, which is pretty cool. Yeah.
On a little different subject, what is the source of your funding?
The US taxpayer. So I actually didn't get to my last slides. I should make sure I show this. So we are a National Science Foundation funded project. We are funded by the federal government, and the reason we're funded by the federal government is for the astronomy itself is interesting. Part of the reason we're funded is for using these discoveries to understand more about the nature of matter. So understand these R process elements, the creation of matter, how these nuclear processes work, how matter is created, but also the technologies we develop as you're doing this. So detecting those binary black holes, you probably, it's difficult to look in 100 years in the future, but I would say 100 years in the future, it's so hard to make gravitational waves that I wouldn't see gravitational waves as being a practical thing. But the things that gravitational waves can discover and the process of discovery is very practical. I mean, spin-offs are interesting. So some of the codes that we developed to look for binary black holes in this noisy data, those computer codes actually found application in the development of denser RAM chips for computers to increase the amount of storage that computers have in the amount of RAM that they have. That we developed some code that is for high-performance computing that had application over there. So there's a lot of spin-off applications in more powerful lasers, better optics, all this type of stuff. So we're National Science Foundation funded. Yeah.
How long did it take to get your grant accepted?
We have very good program officers at the National Science Foundation. It's typically less than a year from submission to.
Very good.
NSF is very good at turning these things around. It's 6 months to a year between submission and finding out that you get the money.
Well, that tells you how important your work is.
Is there any possibility of setting up those indicators in space?
Yes. So I did get a chance to talk about future gravitational wave detectors, but there's a whole gravitational wave spectrum to look at. Just like Arecibo, the radio detector, looks at low-frequency light, low-frequency radio waves. Fermi looks at high-frequency gamma rays. LIGO is the high-frequency end of the gravitational wave spectrum. If you go to a couple of decades lowering frequency, you can't do that on Earth because of seismic noise, but you can put a detector up in space. And there's a plan for a detector called LISA, the Laser Interferometer Space Antenna, that will fly 3 satellites in space, and you'll sense the change in space-time between the satellites. That will get you lower frequency. That will actually get you supermassive black holes in galaxies. You'll see galaxies colliding with that. There's a supermassive black holes at the cause of galaxies colliding to each other. There's another experiment called Pulsar Timing that looks at even lower gravitational waves, and they're trying to see what we call a stochastic background. So this is the unresolved sources. When you get all these sources built up on top of each other, you get a stochastic background, and they're trying to look for that. So there's a whole suite of observatories. Yeah?
Yes, I want to
What's the
ask a
signal?
couple questions, if I may. You said you were trying to locate where in the sky these events were occurring, and we can use parallax, which is taking measurements on, as you know, on either side of the Earth's orbit.
Yep.
That's on the good out to about 15,000 light years. That's within our own galaxy.
Yep.
And so these things are like far away. I don't see how you're getting a long enough baseline to make any
Distance
measurements.
claim?
Okay.
So the distance you actually get, because we understand very well how the amplitude of gravitational waves falls off with distance. And so we have very good predictions for what the waves are going to look like. So the waves themselves tell us how massive the black holes are. So by measuring the waves, the lower frequency of the waves, the more massive the black holes, the higher frequency of the waves, the lighter the black holes. you can measure the masses. And once you get the masses, you can predict what the strength of the gravitational wave should be, and that allows you to figure out the distance. So you measure the masses, and then you figure out the distance from that.
Thank you. And I want to ask also, Kip Thorne and Stephen Hawking were big buddies for many years, and they worked on this black hole, on the black hole theory development. And about a year before he died, Hawking said, black holes as we perceive them do not exist. And he became a pariah in the black hole community. I wonder if you have a comment on that.
I know. So my PhD advisor was a graduate student of Stephen's, and I know that he was very excited about this discovery. So.
Thank you.
One more question.
What happens when a neutron star combines with a black hole?
That's a great question. So depending on how fast the black hole is spinning and what the mass of the black hole is, the neutron star could either just be swallowed whole and nothing will happen. You'll get gravitational waves, but you'll get no light. Or that neutron star can be torn apart by the black hole, and you'll get an electromagnetic signal that won't look exactly like the neutron star merger, but it will have maybe some things in common. So seeing a neutron star black hole merger and the light from that or not is kind of the next big discovery that's waiting to happen.
Didn't they just discover that?
There is a possible neutron star black hole, but I wouldn't say that that's certain yet. Yeah.
What's the experimental evidence that gravitational waves travel at the speed of light?
So with the neutron star merger, you can actually place a constraint on the speed of propagation of gravitational waves, because you know that 1.7 seconds might seem a lot, but it's traveled from 40 megaparsecs away, so it's traveled a large distance. And if gravitational waves and light traveled at different speeds, the light from the gamma rays from the merger were released 1.7 seconds afterwards, and they started traveling towards us at the speed of light, and the gravitational waves are also traveling towards us. So you can use that as a benchmark. So the constraint on the speed of gravity at large distances comes from comparing the arrival time of the gamma ray bursts to the gravitational waves. And there's pretty good constraints there. It also comes from if gravity didn't travel at the speed of light, you get different dispersion in the gravitational waves from the black holes. You have constraints there. But that's the experimental constraints on the speed of gravity speed of gravitational waves come from these types of observations.
Thank you. Our next talk will be at the end of September. Please watch our website, friendsofthegoleta-valley-library.org, to see what we're doing. We're going to do art history in September, probably something on the Maya or another scientific talk in October, and for sure a talk on chocolate with samples in November. So I am sure that one will be packed. Refreshments in the back. Thank you very much to Professor Brown for the wonderful